Okay, welcome back everyone. We're going to wrap up our discussion of linear momentum by talking about the motion of a system of particles. So, what are we trying to get out of this? Well, we just spent a lecture talking about the center of mass of a system, and now we want to use it to see how we can more easily solve momentum problems. Okay, so if you have a problem that involves a system of particles, you can simplify your problem by considering the motion of the center of mass. And if all the forces in the system are internal, the motion of the center of mass will not change. Okay? So if you have an external force that acts on all the particles, you can simplify this by considering that it acts on the center of mass. So F net equals ma, but that works on the center of mass. So, for example, you have Romeo sitting in the back of a canoe, 2.7 meters away from Juliet, who sits in the front. So here's the canoe, and here's Romeo, and here's Juliet. The canoe has a mass of 80 kilograms. Juliet moves to the rear to kiss Romeo. Aww. How far does the canoe move forward when she does this? And we're going to assume that this canoe is symmetrical. Okay? Well, this just means that since F external is equal to 0, this means that x center of mass before the collision will be equal to x center of mass after the collision. Now, why does this happen? Well, this occurs because A center of mass is equal to 0, which means that V center of mass, the change, remains 0, and if it starts at rest, it ends at rest, and that leads to this. Okay, so initially, the center of mass was Romeo's mass times his position, and we'll say at the back of the canoe is x equals 0. Okay, and excuse me, Juliet is going to be at a distance of 2.7 meters, and the canoe itself is going to have a mass of 80, and that's going to act in its geometric center. We then divide that by the total mass of the system. So that's going to be 77 plus 55 plus 80 is 212. And so that means that the x center of mass is simply going to be at about 1.21 meters. Now that's going to remain constant, so that's going to be equal to x center of mass final. Okay, so what's going to happen when Juliet goes to the back of the canoe? Okay, well, we can basically look at this from Romeo's perspective. So then x of Romeo and x of Juliet are both equal to 0, which makes it really easy. So x center of mass final is 77 times 0 plus 55 times 0 plus 80 times x final of the canoe divided by 212. Okay, so now we do this, and that's going to be equal to 1.21, which means that x final of the canoe is now 3.21 meters. So the canoe has to move forward quite a bit to take into account the fact that Juliet has moved backwards. Okay, so that's how we do center of mass problems. And there's actually one more thing that I want to show you, and this is something useful for solving elastic collisions. Okay, so this is actually a quick way to solve elastic collisions using the center of mass of the system. Okay, and remember we had a problem earlier where a 1.5 kilogram object moving at 1.5 meters per second hit a 0.5 kilogram object, and then they moved off in two different directions. So this was from a couple videos ago. Okay, but we wanted to find V1F and V2F. Now, if you do this, that's 0.5, not 1.5. If you do this using a special technique, you actually don't have to go through solving a system of equations. So this is called the center of mass technique, and this only works for elastic collisions. And basically the first step that you want to do is you want to find the velocity of the center of mass of the system. So that's 1.5 times 0.5 plus, times 1.5 plus 0.5 times 0, all divided by 2, and that's going to be 1.1. Actually, it might be easier if we do this in fraction form. That's going to be 3 halves, and 3 halves is going to be 9/4, so 9/8. Okay, and we'll call this 3 halves, which is 12/8. Okay, so the second thing is you need to convert the VI's to what we call the V center of mass frame of reference. So if you imagine that there was an object here moving with the speed of the center of mass, what would V1 initial be as seen from the center of mass? What would V2 initial be? Well, in order to do this, you just have to basically take, so V1 center of mass would be equal to V1 initial minus V center of mass. So that would be 12/8 minus 9/8, so 3/8. And that makes sense because if I'm in the center of mass and I'm moving with the speed of 9/8, and this guy is moving at a speed of 12/8, then it looks like it's moving 3/8 from the perspective of the center of mass. And likewise, V2 initial minus V center of mass is going to be 0 minus 9/8. So V2 actually looks like it's moving backwards to start with. Okay? Now we're going to use the fact that K initial is equal to K final to calculate V1 final center of mass and V2 final center of mass. So this is actually V1 initial, and this is V2 initial. Okay? And here's the really tough part about these problems. You just slap a negative sign on V1 initial center of mass. Okay, so this one will be negative 3/8, and this one will be positive 9/8. All right, so far so good. Now the final step is to convert V final in the center of mass frame back to V final in what we call the lab frame. And notice that what we did before was we subtracted the center of mass. So now to get V1 final and V2 final, we're just going to have to add it. So take V1 final center of mass and add V center of mass. So it's going to be negative 3/8 plus 9/8, and that's going to give us 6/8, which is exactly what we found doing this the long way. And I'll show you that slide in just a second. Okay, V2 final is going to be V2 final center of mass plus V center of mass. So that's going to be 9/8, okay, plus another 9/8, which is 18/8, which is 9/4, so that's 2.25, which is also what we found doing this the long way before. Let's take a real quick look back at that. Okay, and we scoot back, and where was that? That was back here. So I don't know if you saw this video, but this was the long way to solve that problem, and we found 0.75 and 2.25, and that's exactly what we have here. Okay, so this is called the center of mass technique for elastic collisions, and just to quickly summarize what we did here, the first thing that we did was we calculated the center of mass of the system. Then we converted those into a frame of reference of the center of mass. We flipped the signs, and then we converted back. Okay, so this is actually a huge time saver, especially if the two objects are moving toward each other, because you'll have all sorts of issues doing this using the long way. Okay, so I want to make sure that I show this to you. Okay, so that wraps up this unit, and next time we're going to start talking about rotation.